Mhm. Let's make sure. Can everyone see it?
Yes. Okay,
Okay,
go
cool.
ahead. I'll
Yep.
wait a couple seconds.
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. This is Bruce Lung with the U.S. Department of Energy's Better Buildings, Better Plants program. I'd like to welcome all of you today to today's edition of our Better Buildings webinar series. In this series, we profile the best practices of Better Buildings and Better Plants Challenge and Alliance partners and other organizations that are working to improve energy efficiency in their facilities. Today's webinar is entitled Energy Efficiency and Water Savings Are a Combo Deal. Basically, in industrial and commercial buildings, we look at everything from the building envelope to the motor-driven and thermal systems in the processes to find opportunities to increase energy efficiency. But what about the water used in all these buildings and plants? This webinar will explore how saving energy can save water, but also how saving water can yield energy savings. Today, we've got a great lineup of panelists who will discuss the water energy nexus and how to capture water savings from energy efficiency projects, as well as some energy savings that can result from improvements that are intended to save water. Lastly, we will wrap up with a question and answer session and remind everyone about some upcoming events. Before we get started with our presentations, I want to remind our audience that we will hold questions until near the end of the hour. Please send in questions through the chat box on your webinar screen, and throughout the session today, we'll try to get to as many of them as we can. I'll also remind you that this session will be archived and posted to the web for your reference. Next slide, please. I would like to introduce all the presenters in due time, but today I'm going to introduce the first presenter right now. It's Dr. Prakash Rao. Dr. Rao is a Principal Scientific Engineering Associate with the Energy Technologies area at the Lawrence Berkeley National Laboratory in Berkeley, California. Dr. Rao conducts research and analysis into the potential for reducing the energy consumption and water use impacts of the U.S. manufacturing sector while maintaining productivity. Dr. Rao received his doctorate in mechanical and aerospace engineering from Rutgers University and a bachelor's in mechanical engineering from Carnegie Mellon University. Next slide, please. Next slide, please. Go ahead, Prakash.
Thank you, Bruce, for the introduction, and thank you all for joining. So I thought today I could start off by just introducing the energy-water nexus at a high level to help tee off the rest of the webinar. So I want to start off by describing what we mean by the energy-water nexus. So throughout our economy, water and energy are two resources that we end up using as services. So what I mean by services, we use these energy and water to accomplish something like heating, cooling, throughout our businesses and throughout the U.S. And in many cases, there's a strong coupling between the energy and the water. So energy is required to extract water from the ground, from the surface, wherever it is. Energy is required to treat the water at the plant. Energy is required to convey it and distribute it to our homes and businesses. Within our plants, energy is required to pump the water around, heat it up, cool it down, and then energy is required to treat the wastewater. And on the flip, water is required for us to access energy and turn it into a service. So water is required for fossil fuel extraction, whether it's petroleum or natural gas or coal. And water is required, for example, at the power plant to generate electricity for certain types of power plants like coal plants or nuclear plants. So this dependency on the two of energy on water and water for energy is that is the water energy nexus. And what I'm showing here is a chart from the U.S. Department of Energy in their 2014 report, The Water Energy Nexus Challenges and Opportunities. And what this chart shows is energy and water flows through the U.S. economy. So on the top in the green is energy. On the left-hand side are the sources, petroleum, natural gas, et cetera, and where it is used in our sectors in transportation, residential, et cetera, and how much is actually used and how much is lost as you go to the right. And on the bottom, we have the analog with water, the sources, where it's used, and where it's discharged. And as you can see there, the Department of Energy has mapped over how much energy and how much water is used for each of these sectors and for each of these purposes. Now, the relationship between the two is what we call the water energy nexus. So not every quad here is used for every billion gallon and vice versa, but there is a relationship, and understanding this relationship, or the water energy nexus, helps us better manage our resources, these two resources. Where are there opportunities to reduce both? So if you do an energy saving action, is there water savings? Or what are the penalties? If you're doing an energy saving action, is your water bill going to go up, or vice versa? These are things we need to understand in order to make more comprehensive decisions with resource management, and that's what the Water Energy Nexus can do for us. Next slide, please. So as a real example, this Water Energy Nexus stuff isn't sort of highly academic, just to show you it in play. In my home state here of California, in April 2015, Governor Jerry Brown mandated a 25% reduction in water use in response to the severe drought. Well, 19% of all of California energy consumption is related to water. That's not just, that's in treating the water, conveying the water, using it at home or in our businesses. And what the University of California, Davis, their Center for Energy, Water and Energy Efficiency put together is they looked at the data. They looked at, well, how much was the energy savings from the water conservation mandate? And they looked at one quarter, July to September 2015 of the same year of the mandate. And the results were make the point about the Water Energy Nexus in spades. So if we looked at all this energy savings from the utility programs in the state implemented over that same quarter, that same time period, they equal the energy savings from the water mandates. It's about 460 gigawatt hours over that time period. So for that one measure of reducing water use by 25% throughout the state, we saw an equivalent energy savings that equaled all the energy efficiency incentive and rebate programs implemented in that same time period. So it's a pretty substantial impact there. Next slide, please. And now what I want to do is talk a little bit about at the system level, where do we see this energy water nexus in your businesses? Where might you see this? So the first right off the bat is pumping systems. So pumps are used to pressurize and distribute water. Using first order or using principles of physics, what we know is back of the envelope, the energy required for a pump to move water is related to it goes with the cube of the flow. So what does this mean? So if the equation there in the middle, think energy required on the left, flow on the right. If I double my flow in my facility, if I'm following just the principles of physics, that's going to be an 8-fold increase in the energy consumption. Whereas on the other hand, if I half the flow in the facility, it's going to be a 1/8 of the energy consumption. And that's what the cube power does. So there's a strong power with these affinity laws, but it shows that relationship between energy and water. Now, in reality, it's not exactly a cube, and you're not always going to see these savings or these increases. It depends on your pump system and the design and the pump itself and your distribution network. The Advanced Manufacturing Office at Department of Energy has some wonderful resources to help explain the more technical details, which we won't go into today, but one of the last slides at the end of the webinar, you'll have a link to learn more about that. Next slide, please. Another example of the Water Energy Nexus within your businesses and facilities, so cooling towers, and in this case, very specifically, evaporative cooling towers. Here is a great example of water being used as a service. Now, water, we drink water, but much of the water that we use is actually as a service, and in cooling towers, what we're doing is we're taking water and we're using it to cool down our buildings or processes. So warm water is going to come from the condenser, and a pump is used there. It trickles down in this evaporative cooling tower, and a fan is going to pull air over it. So what's happening is essentially energy is enabling the use of water as a service. The fan is allowing for convection over the water, which cools it down, and then it's pumped around. And if you look at a 500-ton chiller operating at minimum efficiencies per ASHRAE, about 15% of the energy consumption is for this system is for the cooling tower. So it's this trade-off is something that one would need to understand. Next slide, please. And the last example on the equipment side that I want to walk through is steam. Steam, again, is water being used as a service. We're taking water, we're heating it up, boiling it, and then using the steam for its thermal energy to power something, to dry something, to heat something. Steam is a very significant energy consumer in our manufacturing operations. 31% of on-site energy use, 11% of on-site water use by one estimate. Next slide, please. Next slide. Oh, thanks. So what I wanted to do with the steam system is kind of show the idea that energy saving actions will lead to water savings as well, particularly in the steam system. So I wanted to highlight, I put together this mock steam system. It's 100,000 pounds per hour, 150 psi steam. And it's just some typical things that energy saving opportunities in steam systems. What's the water savings? We don't often think about the water savings. So if we look at the steam system, it's pulling in about 45 million gallons per year of makeup water. And we have some parameters here. Let's say 30% of the traps steam traps are broken. Common measure is fix your traps. It's returning 70% of its condensate. 80% recovery is about best practice. That's blowing down about 10% of its water. So there's energy savings associated with remediating these actions, but what are the water savings? So if you go to the next slide, please. Increasing the condensate recovery. So we're at 70%, which means 30% of the water is not returning back to the boiler to become steam again. And the challenge here is that water is very warm versus the makeup water is very cold. So you're losing a lot of thermal energy. So best practice is increase your condensate recovery. Let's say we go from 70 to 80%. In this example, you'd save quite a bit of energy and the associated energy cost savings, 31,000 MMBTUs, but you're only still going to save 10 million gallons annually of water. So substantial water savings by increasing your condensate recovery because you're losing less water. Next slide, please. Reducing blowdown from 10 to 5%. So blowdown, periodically, you have to drain the water to maintain quality requirements. Doing this too often, it can lead to energy losses, but it also leads to water losses. So in our example here, if we go from 10 to 5%, 5% is kind of like a best practice. You're losing all that thermal energy when you're blowing down, and by reducing it to 5% blowdown, you're saving energy, but you're also saving 6 million gallons of water per year, which might not have been in the calculations. Next slide, please. And then finally, fixing traps and leaks. So steam traps are devices along your distribution system, which are going to separate the steam and the condensate as the steam condenses traveling around. Traps that are broken up and open could just bleed out steam. The system that I've put together, you have 30% broken traps. Let's say we drop that to 10, which is about a reasonable number. Going to have substantial energy savings, 20,000 MMBTUs, but you're also going to save about 1.6 million gallons annually. So again, water savings accompanying this energy saving action. Next slide, please. So in all, if you look at these three measures, returning more condensate from 30% to 20%, reducing your blowdown by half, fixing a lot of your broken traps, you're going to see a lot of energy savings. But you're also going to, in this case, hypothetical case, we reduced our water use by 40%, all through these energy saving actions. So as far as resource management, this is something that to consider as you do calculate the ROI, for example, on some of these measures. And I should mention there's also chemical savings and other savings. We're just looking at the energy and water here. Next slide, please. So here's what the system looks like afterwards. In the interest of time, we could just go to the next slide. Now, that was a hypothetical example, but here's a real world example. So Harvick is a Better Plants Challenge partner, both in the energy and the water program, a leader in sustainability. They're a plastics manufacturer in the Rochester, New York area. They have a great story where they were hit with higher fire insurance premiums unless they could increase the water service to their facility. They couldn't increase the water service to the facility, so we're going to be hit with a $50,000 fire insurance premium increase. Well, the folks at Harvick said, hey, why don't we build a rainwater pond? So they built a 900,000 gallon rainwater retention pond, and what that does is it appeased the fire insurance folks since they save that $50,000. But they're also using it as a heat exchanger. They have a heat exchanger in there, and they're replacing cooling towers with this pond water. They're sending their warm process water to the pond, cools down, goes back to the plant. They don't need the cooling tower as much. So this was a fire insurance savings project, but it's also saving 145,000 gallons per month in water because you don't have to use the cooling tower. And it's also an energy saving project. It's saving 17,000 kilowatt hours per month in energy savings because now they had 50 horsepower worth of cooling of pumps and fans attributable to the tower down to 6 horsepower. So simple financials, you have $50,000 in avoided insurance costs, $3,000 in water costs. We had substantial energy cost savings, but we didn't have the firm numbers around those, and it had a $250,000 implementation cost. But multiple savings, definitely 2 for 1, 3 for 1 when you look at the fire insurance as well with this project right here. And more information on this can be found on the Solutions Center, and there will be a link to that at the end of the webinar. Next slide, please. So, so far I've been kind of talking about the water energy nexus within your businesses and facilities, but I wanted to also discuss the water energy nexus outside your facility. So energy is involved in bringing water to your facility and taking it away and treating it, and we might not always appreciate this. So what we've done here is kind of piece together where we could the amount of energy required to bring water to our facilities and to treat the wastewater. Nationally, for municipal water, let's say it's surface water, it's about 1,600 kilowatt hours per million gallons for treating water, and then about another 750 to 3,000 kilowatt hours to treat the wastewater. So you're looking at about 2,500 to 5,000 kilowatt hours per million gallons of, that you use at your facility for treating the water, bringing it to your facility, and then treating the wastewater. So substantial energy requirements outside our facilities for the water we use. And I also want to point out geographically, you look at Southern California, where the national average is 1,600. In Southern California, the national average is over the regional average is over 10,000 kilowatt hours per million gallons. So regionally, these numbers change, and it's important to know to understand that. Next slide, please. So we just saw that there's going to be additional energy savings. So every gallon you reduce, or every million gallons you reduce, the amount of energy you're going to save on the water supply and on the wastewater treatment. There's also something that water savings also actually grows. So for every gallon you save at your facility on average, you're saving about 1.16 gallons at the source, because there's about a 14% loss in our water supply systems nationally. And this can be as high as 40% in some areas, and some as low as single digits in other areas like Las Vegas and Austin, Texas, where they really need to keep close tabs on their water use and not have loss. But for water you're saving at your facility, you're actually going to be saving more water throughout the system, and that more water is less energy. The more water you're saving is less energy required to treat that water, convey that water, distribute it, etc. And finally, there's also water savings at the power plant. If you're doing electrical projects, electricity saving projects, you may have water savings at your power plant. Next slide, please. And this figure here just quickly illustrates that's put together by the National Renewable Energy Laboratory. So if you look at, for example, the second bar from the left is the coal using a once-through cooling system. If you save a megawatt hour at your facility, you're going to save about 37,000 gallons of water at the power plant if you're getting your electricity from a coal-fired plant with once-through cooling. So water savings from your electricity savings. So that's my overview of the water energy nexus and all its implications. I guess the 2 points that I want to leave you with is that understanding the water energy nexus can really help you with your resource management strategies and understanding and making more informed decisions about resource management. And also the water energy nexus will extend beyond your facility. There's water savings at the power plant. There's energy savings in the distribution system. There's energy savings in the wastewater treatment system. So it's really ensnares all of the United States sort of energy and water use. Next slide, please. That's it. Thank you.
Thank you, Prakash. Very illustrative presentation there. Next slide, please. Next, I'd like to introduce Mark Denon, who is the Director of Energy and Environment at Cummins, Inc. Some of you may know the name Cummins from generator sets and engines, and that's exactly the company he's from. Mark leads the energy, climate change, and eco-efficiency initiatives for Cummins global facilities and operations. Mark has over 30 years experience at Cummins leading the energy, environmental, health and safety, and materials engineering programs at site, business unit, and global levels. He received his Bachelor of Science in Biology and Master of Science in Environmental Engineering from the University of Minnesota. I should also point out he is joined by Nicole Morris, one of his colleagues, who will be able to help answer questions on their successful water and energy efficiency programs. Next slide, and go ahead, Mark.
Well, thanks, Bruce, and hello, everyone. So today I'll be talking about how we approach energy and water conservation at Cummins. And what I'll be doing is providing some real-world examples of the concepts that Prakash covered very well in his talk. Next slide, please. First, a little bit about Cummins. So as Bruce mentioned, we're probably best known for making diesel truck engines, but we also build diesel and natural gas engines for bus, train, marine, mining, and power generation markets. We also make generators, components like turbochargers and exhaust emission control systems, and we have a global network of distributors and dealers to service these products. And we are headquartered in Columbus, Indiana. Next slide. So to produce the over 1 million engines per year and other components that we make, we use quite a bit of energy and water. Our operations are not highly energy intensive, but we still consume quite a bit of energy for machining, engine testing, and assembly operations. We're spending about $150 million a year on electricity, diesel fuel, and gas. And by the way, this makes up about 98% of our facility carbon emissions are all associated with this energy use. About half of our global energy consumption is taking place in the U.S. On the water side, we're using almost 1 billion gallons of water per year, and our top 3 water users are cooling towers, irrigation, and for sanitary purposes. Next slide. So at Cummins, we have always focused on our biggest opportunities to save energy and water. And what we've found is that many times we can do both within the same project. So, for example, any changes we can make to lower our cooling tower loads reduce both energy and water consumption. We've been able to upgrade our process and facility equipment efficiency, very important, and as is optimizing how we operate this equipment and these processes. And finally, we also consider the indirect or off-site benefits of saving energy or water at our facilities. So I'll provide examples of each of these opportunities on the next few slides. Next slide. So many of the conventional energy reduction efforts that we've been doing also have the added benefit of reducing waste heat generation. And in turn, that reduces the demand on our cooling tower systems. So for example, we've been upgrading the efficiency of our lighting systems in our plants for years. In some cases, we're on the 2nd or 3rd generation of light efficiency upgrades. But however, lighting still remains a big opportunity for us due to the pace of the technical improvements within the technology. So we've launched a global campaign to implement a common approach to LED lighting by focusing on our biggest opportunities and prioritizing those actions. And along with the energy savings comes significant water reduction, again, through the avoidance of that cooling tower demand. And at Cummins, we also use a great deal of compressed air in our manufacturing plants. In fact, compressed air makes up about 12% of a typical plant electricity consumption at our company. So we've been focused on optimizing compressed air use and compressed air systems on a global base. So most of our plant compressors are cooled by chilled water, and we see significant reduction in cooling tower load when we minimize our compressed air usage, as shown on this slide. Next slide. So we're also implementing some less common technologies that are more focused on some of our unique opportunities as an engine manufacturer. A good example is from one of our most energy intensive operations, which is engine testing. So we burn millions of gallons of diesel fuel each year to develop and produce our engines. So we first focus on eliminating unnecessary testing through more computer analysis and bench testing. But we can't eliminate all of it, so we need to make it as efficient as possible. So when testing engines in a lab setting, we need to simulate the loads the engines will see in service. And dynamometers, or dynos, provide that load to the engine. And if you look at the chart below, you kind of see how the energy from the fuel is expended in an engine. So about 40% of that fuel's energy goes to actually turning the drive shaft. About 30% is lost as heat through the exhaust, and another 30% is removed from the heat from the engine through the cooling system. So only about 40% is doing useful work. So so in an engine test, the dynos convert the engine power, that mechanical output, into heat, at least with conventional dynos. So all of that energy tends to go to waste. However, by using regenerative dynos, we convert that power to electricity, which we can then use to power our facilities. So we're able to recover a good portion of the energy from the fuel. So along with that electricity conservation, or energy conservation, we also reduce the load substantially on the cooling towers. So we typically see over a 50% cooling tower load reduction with this process. Next slide, please. So another focus that we've had is incorporating energy efficiency into new building construction. So we've now integrated that into our building standards to help ensure efficient performance from day one. And a good example of that is our new office tower in downtown Indianapolis. In this case, the narrow profile of the office building, along with its orientation, maximizes environmental performance. And this is through using high-performance glazing with exterior shading, high-efficiency lighting, office daylight controls, demand-controlled ventilation, exhaust air energy recovery, and a variety of other technologies. Along with reducing the heating and cooling loads, the shape of the building allows every worker to have direct access to natural light. And the facade of the building is a varied grid of glass and metal fins that are calibrated for the particular shading and daylight needs of each face of the building. And not only does that reduce energy and cooling water consumption, we've also incorporated stormwater collection at the site. So a green roof on the parking garage and the terrace is collected in a large 200,000 gallon cistern, which is then used to water the green space, trees, and plants. And it also helps keep over 80% of the rainfall on the site and away from the city's stormwater system. Next slide, please. We've also achieved major reductions in energy and water consumption by upgrading older, inefficient facility equipment. A good example of that was the replacement of an old cooling tower system at one of our big engine plants. The new towers reduced water consumption by 38% compared to the previous system by reducing leakage, reducing drift, and through higher efficiency cooling. The tower electricity consumption was reduced 19% by improving fan efficiency and reducing pumping loads through a modular approach. And finally, the new towers also produce much cooler water, which improves the efficiency of the chiller plant by 25%. So win-win all around. Next slide. Another example is replacing old steam boilers at one of our sites with high efficiency hot water boilers. In this case, at this site, we had eliminated most of the need for steam in our manufacturing processes. So we were able to replace the oversized, inefficient steam boilers with right-sized, high-efficiency condensing hot water boilers. And these units are microprocessor controlled to provide an infinitely variable supply of hot water that is much more closely matched to the actual demand. Next slide. So we've also been pursuing renewable energy. We've installed now 14 solar arrays at sites around the world, totaling about 8 megawatts. But we're also looking at what we can do off-site. And this summer, we signed our first agreement to expand a wind farm in northwest Indiana near Lafayette, adding 75 megawatts of capacity, about 30 wind turbines to the wind farm. This expansion will generate the amount of electricity that we use in Indiana at our various facilities in that state. And the wind farm will be completed about the end of 2018. This is a 15-year agreement. It will reduce, it'll produce about 260,000 megawatt hours of clean energy per year. And the utility water savings are huge, 69 million gallons of water per year. Next slide. So, as I mentioned, we're also focused on optimizing performance of our existing equipment. So we do that by ensuring we've got capable energy and facility managers at each facility. And we do this through our environmental champion program, which we deploy training and common tools, share best practices, and really leverage our internal capabilities. Next slide. And with this approach, we've been able to commonize how we manage both energy and water. And when you think about it, there are many similarities. We use balances to visualize our energy and water consumption. We can do leak elimination practices for each media, do treasure hunts to find low-cost, no-cost opportunities, and have shutdown plans, and so on. And you can find a lot more detail on our champion program on the Better Buildings website shown on this link here. And finally, last slide, we have also implemented a capital project hopper to gather all of the opportunities across our company for energy and water consumption reduction. And by putting these in a common hopper, we're able to prioritize based on the best return on investment and the best environmental impacts for given projects. So through that, we're able to implement improvements across the company in the most practical and efficient way. And last slide. So thank you for that, and I look forward to your questions. Bruce?
Thank you, Mark. That was very great. Next slide, please. At this time, I'll go ahead and introduce our third speaker. It's Richard Demerjen, who is the Assistant Vice Chancellor of Environmental Planning and Sustainability at the University of California, Irvine. In this role, Richard oversees campus-wide sustainability programs, environmental planning programs, and physical and community planning for UC Irvine. Richard has a bachelor's degree in landscape architecture from the School of Environmental Design at California State Polytechnic University, as well as an MBA from the Paul Merage School of Business at UC Irvine. He is also a registered landscape architect in the state of California. Richard, please take it away.
Thank you. I'll be discussing a project under construction at UC Irvine that provides some examples of the water-energy relationship on a university campus. This is a collaborative project between UCI and Irvine Ranch Water District, our local water provider, to convert our central plant cooling towers from potable water use to recycled water use. The project relies on an innovative business model to achieve significant savings in both the embedded energy of UCI's water supply and also the amount of potable water consumed on the campus for energy production. Next slide, please. For a little bit of background, we're a public university located in Orange County, part of the 10-campus UC system. It's a large campus, about 1,500 acres of land area. We have about 11 million square feet of building space. Being located in the Southwest, water resource management and drought resilience are key concerns on the campus, as well as energy management and greenhouse gas mitigation. We currently consume about 360 million gallons of potable water per year. A significant amount of this is used for energy production on the campus. We use about 140 million gallons of recycled water currently on the campus, primarily for campus landscaping. So currently about 28% of the water that we use on campus that's consumed as potable water is returned to the campus as recycled water for beneficial use on the campus. Next slide, please. Within the University of California system, we have far-reaching sustainability and water policy. Each campus maintains a water action plan that addresses our water resources management and water conservation goals and projects for the campus. UC-wide, each campus has a per capita water conservation goal of reducing water use to basically by 36% over a 3-year baseline year. And our campus has adopted a stretch goal of pushing that to a 50% reduction. So by 2025, our per capita water use would be 50%, of our baseline year. So we're currently on track to meet that. We've had a lot of positive water conservation projects on campus, but as we continue to grow as far as program and facility growth, it'll be difficult to maintain that. And then the increment of going from 36% to 50% will be significant. Next slide, please. We're very fortunate to be served by the Irvine Ranch Water District, which is a good partner to the campus. IRWD has been a pioneer in many areas of water resource management, including early development of recycled water systems dating back to 1967. UCI has participated with IRWD in the recycled water program since its inception in 1967 and continues to be one of its largest customers. In 2015, IRWD did a detailed assessment of the water energy nexus of our water supply, both for potable water and recycled water to the campus. So it provides the campus and all of the customers in the district with a good understanding of the embedded energy in water that's consumed on the campus. Next slide, please. UCI's sewer flows are treated at IRW's Michelson Recycled Water Treatment Plant, which is about a mile from the campus. It's a state-of-the-art treatment plant that has undergone recent expansion and upgrades, and it includes on-site generation of carbon-free electricity now with the biodigester as part of their biosolids treatment program. So that'll come online next year. So part of the energy in the plant will be generated through renewable sources. What the plant provides is tertiary treated and disinfected wastewater under California Title 22, which in California can be used for certain indoor and outdoor non-potable water applications. So the treated and disinfected wastewater is then purchased by UCI at a cost savings below the potable water rate and used on campus. And currently, we use the water for outdoor uses, primarily landscaping and also things such as street sweeping. Next slide, please. We have a history of collaboration with IRWD, again dating back to the 1960s. Over the past several years, we've done some very good collaborative projects as far as water conservation on the campus, which has resulted in about 78 million gallons per year of water use reduction, which has played a big part in us being able to achieve that 36% water reduction and track online as far as our water use goals. Next slide, please. UCI is powered by a central energy plant, which includes a combined heat and power system for the cogeneration of electricity and thermal energy. The plant includes a large thermal energy storage tank and 2 sets of evaporative cooling towers. The cooling towers consume about 80 million gallons per year of potable water. So energy production of the plant is our single largest potable water consumer on the campus, which accounts for 22% of our potable water use. So as the largest user of potable water on the campus, converting the central plant to recycled water has been a big priority in our water action plan and is a project that the campus has been looking at for several years as far as the potential for implementation. Next slide. So our project has basically two elements. We have a recycled water pipeline, a dedicated 12-inch recycled water pipeline that'll serve our central plant. That pipeline is being funded by IRWD. Because of the large volume of water, it required a dedicated pipeline rather than connecting into our existing recycled water distribution systems. The second part consists of improvements at our central plant, which are essentially plumbing improvements to receive and monitor the recycled water as it comes onto the campus. The central plant improvements will be funded by the campus in a method that I'll discuss a little bit later. And the connections at the plant will also need to address how we'll treat the recycled water, which has a different water chemistry than the potable water that we currently receive. Next slide, please. So with this project, this will be a large project for us. So when the project's fully online, our potable water savings will be at about 50%. So we'll be on track to meet our 50% water target. So it's by far the largest water conservation project on the campus. It also put us into a position where nearly 80% of our potable water consumed on the campus will be recycled and returned to the campus to be used for beneficial use. Next slide, please. I mentioned IRWD has conducted a detailed assessment and inventory of the embedded energy in our water supply for both potable and recycled water, and it's specific to our location and elevation, so we feel pretty confident about these numbers. So potable water delivered to UCI has an embedded energy of 4,158 kilowatt hours per million gallons, which would be the energy required to pump, treat, and distribute the water to UCI, and then collect and treat the sewage. And a similar calculation of recycled water use shows an embedded energy of 3,225 kilowatt hours per million gallons. So roughly 933 kilowatt hours of energy is saved per year for every million gallons of water where we convert from recycled use to potable water use. So overall, the project will save approximately 81,000 kilowatt hours of embedded energy through the conversion. So the project will result in a significant reduction in the embedded energy consumed in our water supply, and also a significant reduction in the potable water used on the campus for energy production. Next slide, please. So as far as the business model, it's been our experience that water conservation projects are more difficult to finance than energy projects, as they generally have a much longer payback period and rely on significant rebates. And a lot of this is due to the cost of water versus the cost of energy. So UCI and IRWD address the challenge by funding the central plant improvements using an on-bill financing approach based on the cost differential between potable water and recycled water, where the commodity price of IRWD's recycled water, which is 40% less than the potable water rate, comes into play. We did receive a grant to offset about 25% of the capital costs for the on-campus improvements, and the remainder is being financed through this on-bill financing with the cost differential. We're currently estimating that the capital costs will be paid back in about 8 to 9 years, and at that point, once the capital cost is paid off, UCI would then begin to pay the lower recycled water commodity rate, which would result in annual savings to the water commodity costs. So in the upfront years, we'll continue to pay the potable rate until the capital cost is paid off, and then we would revert to the recycled rate once the capital cost, the improvements are paid off. Next slide. And just in closing, as far as our next steps, I mentioned we're currently under construction with the project on schedule right now to start up in February of 2018. Next slide. Thank you.
Well, thank you very much, Richard. It was an impressive presentation. It's really good to see all the things y'all are doing over at UCI. Next slide, please. Before we take questions and answers, I did want to point to some additional resources that our speakers have provided for us today. The first one among those is this document you see, Developing a Corporate Water Management Strategy for Manufacturers. Prakash may have been a little modest earlier, but he was actually the lead author and researcher on that document, and it really details a lot of good tools and resources that particularly for large energy and water users like manufacturers can help them, really focus our efforts and look at, managing the risk from water consumption. We also have the Harvick Showcase project. Harvick is a Better Plants Challenge partner, and that showcase is up on the Better Building Solutions Center. We also have a showcase project from Nissan North America, one of our Better Plants Challenge partners, that details their water energy saving efforts. We also have some additional resources through the Advanced Manufacturing Office here at AMO or at DOE. The Advanced Manufacturing Office within the ERE is where Better Plants lives, and so we developed some pumping system resources, source books, various fact sheets, the pumping system assessment tool, and we also did the same thing for steam systems. We had a long-standing steam program a number of years ago, and we developed a steam system modeling tool, steam system source books, as well as a bunch of case studies and fact sheets that really discussed the interplay between the water use and the energy use in steam systems, particularly for the feed water pumping system. So with that, next slide, please. We'll go right to the question and answer session, and we did get a few questions in here today. I'm going to give a couple right here to Prakash that came in. The first one was, he's going to answer both of them at once. For electricity generation, doesn't water get taken out of a water body, but most is put back even at a higher temperature? And then the second question is, can you comment on evaporative cooling and the overall effect on water use? Prakash?
Sure thing. Thanks, Bruce, and thanks to those who asked those questions. They're really great questions and very perceptive. So to answer the first question, yeah, electricity generation, it depends. What I described in the presentation was once through cooling, in which case the person asking the question is exactly right. The water is going to come in, cool the condensers, and then go back out to the river or whatever the surface water discharge point is, and at a higher temperature. The caveats, though, I would say are couple-fold. One is in California, for example, that's no longer going to be allowed, what's called once-through cooling. You're going to have something called a cooling tower or recycling closed-loop system, which then leads to sort of the second question about evaporative cooling. And there what you're doing is where the once-through cooling system just takes in cold water, it gets warm, and that's how the heat is dissipated. An evaporative cooling system will evaporate the water, which you get a lot more heat transfer when you go from water to water vapor. And that's what a cooling tower does. And now the difference here is a point that, water researchers and folks in the water world are probably familiar with these terms of water use and water consumption. They're different. Use is a general term, I mean, anytime you use water. Consumption is that, consumption is that amount of water that you're using, but you're not returning back to the point of source. Evaporative cooling is the consumptive water use. Bottled water is a consumptive water use. And these, some would argue, in terms of watershed health, these consumptive uses are the most important ones to pay attention to because you're depleting the sources in the area that we all share. So, that would be on evaporative cooling, the electricity generation. Yes, once through cooling does do that and returns water to higher temperature. The other caveat I want to point out, in addition to California not allowing it, that river water gain. You want to keep rivers, I think it's like 32 degrees Celsius to kind of keep all the fish and everyone else happy. There's a recent study that something like over 50% of United States power plants and thermal generators are at their peak temperature disposing water to the rivers at higher than 32 degrees Celsius. And there's times even when the river temperature is higher than 32 degrees Celsius just naturally because it's so hot out, and you can't use that water. So the thermal pollution, the higher temperature is an environmental concern. But I hope that answers the questions, and if not, please ask more in the chat box.
Sure. And thanks, Prakash, for answering that. And also, I'll remind everyone that feel free to send in some questions if you want to right now. The next question is going to be for Mark and Nicole. The questioner asked if there was any downside to converting from steam boilers to hydronic boilers.
And Bruce, the answer to that is there were no downsides that we're aware of. But you need to keep in mind that this project was both about replacing, quite old, 47-year-old equipment that was not very reliable, but also about matching the heat requirements with processes at the plant that had changed over time. So really, it was old equipment that wasn't appropriate for the new usage requirements.
Okay.
So, but the benefits we saw include, much lower energy consumption by, having infinitely variable combustion air fans, less pumping energy, less auxiliary equipment, low NOx emissions, lower maintenance, accelerated hot water response time, which was a big improvement, and smaller physical footprint. We actually freed up some space at the site.
Okay, very good. I think I'm glad you mentioned that, because that's one of the things that doesn't always happen when you have new process lines or new configurations in the manufacturing plant. You kind of need to take stock of what you have in terms of the cross-cutting and supportive equipment to see if it's still appropriate or if it's oversized, and see if there's any opportunities to either right-size it or change it up a little bit, like the way you all did. Next question we have actually here is for Richard, and the person asking the question said, does IRWD have testing procedures where you do not have to shut down the potable water lines to a site?
Yeah, IRWD, they do have testing procedures at their plant, and also we will be testing the water quality at our plant. What we're doing for our project is we're retaining the potable water lines to the project, so that we will have basically dual feeds to the project, so that we will receive and use recycled water. But if there's ever a concern with water quality or other issues at the recycling plant, we have potable water lines that'll serve the site. So we're going to have basically dual water service.
Okay, and then another question that came in for you was, what is a weighted campus user? Is that like your normalization metric? Or?
It is. It's basically a weighting factor that's used by universities and mainly in sustainability metrics. It was developed by ASHE, which is the Association for Advancement and Sustainability of Higher Education. And it basically weights campus population for residential versus non-residential population.
Okay, interesting. Okay, very good. Still fielding a few more questions in here. One thing I wanted to pose real quick for both Mark and Nicole and Richard. One of the things that we've noticed, both in industrial and commercial buildings end users, is that some of them have some pretty aggressive water reclamation programs and initiatives going on. And I wanted to see if y'all are looking into that, or if you've already done that as well.
Yeah, so at Cummins, Nikki is leading a very interesting project to reclaim wastewater for reuse inside our facilities, if that's kind of what you're talking about, Bruce.
Yes. Go ahead.
Nikki, if you're on the line, could you expand on that a bit?
Yes, we have been partnering with a group called Sustainable Water to develop a reclamation program for our industrial and sanitary wastewater. Our pilot site is one of our largest manufacturing facilities within Cummins, and we should have construction completed sometime mid-year next year, and it would reclaim around 15 million gallons per year of water that would traditionally be discharged to the local municipality for disposal. Mm-hmm. So we would recycle that water and use it in non-potable water areas throughout our facility for coolant systems, for machining. It's a high machining manufacturing facility, so they use quite a bit of water for coolant systems in wet machining processes. So we would be able to reuse that water in that, and additionally we would be able to reuse it in our coolant tower, which is the largest user at that particular facility. And we're looking at, that will be our pilot site, and if it goes well there, we are looking at doing the same thing at one of our Jamestown locations and potentially expanding that and some of their engineered wetlands for some of our areas in overseas.
Okay, great. And Richard, for you?
Yeah, currently we're not doing any on-site reclamation. We've looked at different, projects for doing stormwater capture and reuse, condensate recovery and reuse, but we haven't any projects move forward. We're fortunate that we have the Michelson plant a mile from the campus, so kind of for us, as far as economies of scale, it makes a lot of sense to have the water recycled at the plant by IRWD and have us basically purchase it back. So we're not doing anything on site.
Okay, very good. Let's see, there was one other question that came in here. Let me find it here. Somebody had a question about the water in the cooling towers, if you can use reclaimed water versus you have to use potable water. Are there any differences? I don't know, Prakash, you want to take a stab at that?
Yeah, sure. Somewhat speculating here. I would think that the cycles of concentration is more dependent upon the level of contamination in the water once it's been churned through your system. So the incoming water, I would assume, if it's recycled, would have more poor water quality. So maybe initially or something like that. But I would think ultimately, once it goes through the system, it's picking up the same amount of contaminants, and I'm not sure what the effect would be on the cycles of concentration. That's entirely speculative, kind of off the cuff thinking, but welcome our other panelists to chime in and correct me if I'm wrong.
Yeah, at Irvine, the recycled water that's being used is fairly high quality, but it is higher in in turbidity, so it's higher in solids, and there is other water chemistry that's different than potable water. So the filtration system and the treatment system is a little bit more advanced than what we would use for potable water. So that's something that our central plant staff has been working on. Will be the water testing and treatment for the recycled water, which is a little bit different. So the different chemicals that'll be used.
Great. Well, thank you very much, Richard. Mark, did you want to jump in, or?
Yeah, just one last thing. So we're recovering condensate at a number of our facilities, and that's an excellent feedstock for cooling towers. It tends to be very low in mineral content. It's essentially distilled water. So you generate much less concentration through that process Prakash described.
Yes, exactly. I was going to mention the same thing at the particular facility that we're doing the pilot reclamation for wastewater project. They reclaim about 300,000 gallons of condensate from their air compressor mechanical room each year, and that goes directly into their cooling tower. And it reduces the pollutant load in their tower, reduces the conductivity. So it's a beneficial stream.
Great. Excellent. Well, thank you very much, Nicole. Next slide, please. We're almost at the end of the hour, and I wanted to give a plug for next month's webinar, which will be how to leverage the DOE National Laboratories. As you can see here, Secretary Perry described the national labs as the crown jewels of America's R&D efforts. This panel will actually be very interesting because it'll be moderated by my colleague and the program manager for Better Plants, Mr. Eli Levine. And prior to coming to Better Plants, Eli was managing the Clean Energy Manufacturing Initiative, and he also worked on the Technologist in Residence program. So he knows very well, what the national labs can do and ways that, or individuals and companies and organizations in society can work with the national labs. So all that will be detailed, and it should be a really good webinar. We hope you all will come back for that one. Next slide, please. So we want to just give you our contact information. I'm sorry if we didn't get to all your questions today, but please note down our contact information, and you can submit questions to us later. We will be archiving this, and everyone who signed up will get a notice letting them know when it's available, as well as when future webinars will be available. So thank you very much for your attention and for joining us today. We hope it was a very good, valuable webinar for you, and we hope to see you again in the future.